initiative for the Teach for Science program, where number of faculty members and students from across the India are mentoring number of students for various projects. And this lecture series is part of that Teach for Science. I think most of the students who are attending this session are part of that. So either they are mentors or mentees. And this second lecture is by Dr. Neha Sardana. I welcome you, ma'am. I would like to briefly introduce you before we can start with the lecture. Dr. Neha is from Department of Metallurgical and Material Engineering from IIT Ropar. Her areas of specialization are size properties like electrical, mechanical, and optical, the relationship of nanostructured materials for different applications, plasmon-based materials and metamaterials for optical sensing devices, in visible and IR regime. And she is also interested in electromagnetic response studies and gigahertz regime for transmission and receiving applications. She has earned her PhD degree from International Max Planck Research School for Science and Technology, Nanostructures, and Martin Luther University from Germany. And her master's is from Technical University of Denmark. She has a BTech in Metallurgical and Materials Engineering from IIT Roorkee, Uttarakhand. And prior to joining IIT Ropar, she has work experience as a scientist at INST Mohali, Punjab. And also she has served as assistant professor at IIT Jodhpur. She has number of publications, patents, and accolades to her kitty. And I congratulate ma'am for that. And I thank her for taking out time and talking to our students about metamaterials. But before we start, I would just like to briefly say that we have a constraint of 40 minutes here. So we have already talked to Dr. Neha about the timeline. We'll try to wind up the talk in 25 minutes, followed by a 5 minutes of the question answers. So ma'am, it's all yours.
Thank you, Vindhya-ji and INYAS office for coordinating this particular lecture. Thank you so much for having me here. So without any delay, let's start and enter into the world of metamaterials. Am I audible? The very first question is, do you have any background noise or is it clear?
It's perfect.
Okay, great. Let's enter the world of metamaterials. Have you heard this word meta? Yes, you might have heard it, right? Because Facebook is writing it below it, right? Meta. They have changed their name, so Meta. So let us see what is a metamaterial. So many of you have heard about biology, physics, chemistry, and engineering. So if something is moving or not moving, it's biology. If something stops, it's physics. If something stinks, it's chemistry. And if it does not work, of course, it's engineering. But surely if something is beyond all these things, it's meta. So metamaterials are actually materials which are designed to have novel properties that are beyond the normal interactions that is in mechanical, optical, acoustic domains. So if we go back in history, the definition of metamaterial was a man-made synthetic composite material with a structure that it exhibits properties which are not found in nature. So by that, all metallurgists are metamaterial engineers. So naturally occurring, you find copper, you find iron oxide, and we as man, we made brass, we made bronze, we made pig iron. So these must be the metamaterials. Yes, these were defined as metamaterials till a century back, but now the definition of metamaterials is changed. So now the metamaterials are artificial periodic structures with lattice constants, you know, lattices in atoms, that are much smaller than the wavelength of incident radiation. So here we are not talking about lattices at an atomic scale only. We are talking about lattices that we can structure and which are smaller than the incident wavelengths. So supposedly if you're talking about radio waves, then the structure sizes you're talking about are few centimeters. If you're talking about visible range, then you'll have to go to nanometer range periodicities. And these particular metamaterials have a very certain characteristics that they have a negative refractive index. Now you might be thinking, what is this negative refractive index? I have always heard that the refractive index is positive and glass is a refractive index material. I have used water. I know these kind of things. What is negative refractive index? I'll get to it. Before that, I want to tell you about something about nano, because these two concepts are quite closely related. When we talk about metamaterials in the visible range, we need to know about nano. So Richard Feynman was the first person who's considered as the father of nanotechnology. He said there is plenty of room at the bottom. And what did he mean by that? If you talk about man-made things or a human being, he's around a few 1.5 meters or around that. 151 centimeter or something is our normal height. Then if we go below that height, so on a human, there can be millions of ants. So they are around 5 millimeter in size. So if you go below that size, that is often hair. So you can see our own hair has our head has millions of hairs because its sizes are much smaller. And similarly, our body is fulfilled of billions and billions and trillions of red blood cells because they're much smaller in size, that is 2 to 5 microns. So as the size reduces, you can fit in more and more things in the same space. So that is why he said there is plenty of room at the bottom. And when we go to the nanometer scale, you might have heard about carbon nanotubes, fullerenes, and so on. And you can think about how many fullerenes and carbon nanoparticles are we talking about in 1 meter of a human being. So what happens when these structures of some materials go into the nano regime or are very small? What happens because of that? Its properties changes. And if we look back in history, if we go more in our history, so we can see the traces of nanotechnology. The term might be coined now with Richard Feynman in 1959, but this technology was already known to the ancient people. The Lycurgus cup is still there in the British Museum of London. If you visit London, please go and see this. It is a very beautiful nanotechnological aspect cup. It is having a red color when you see it in reflection mode. That is, if the light is inside the cup, and under the reflection mode, you can see the green light. So under transmission, you see red light, and under reflection, you see green color of the same cup. And why is it so? Because it had certain nanoparticles of gold that were mixed in this, and that is why this is giving a plasmonic effect. So if you might have visited Goa churches or any churches around you, you might have seen such kind of beautiful paintings with various colors, green, reds, and blues. And these are nothing but sulfide nanocrystals and gold nanoparticles, silver nanoparticles embedded in various kinds of emulsifiers. And these give the plasmonic effect, and that gives the color of these particular glass windows. And if you go back to 1987, Michael Faraday, who you might be knowing because of all the electrical experiments or electronic experiments, but Michael Faraday was a very good chemist as well. So he was the first person who has documented it to make gold nanoparticles, and they are still very stable at his museum. And you can still see these particular gold colloids, which are pink and red in color. And so nanotechnology as such was known by chemists for a long time. It's just Richard Feynman who gave the name to this particular technology. So we have seen these in stained glasses. We have seen it also when we saw Game of Thrones. And we have seen the nanolloid steels there, where the Valyrian steel could kill the White Walkers. So before we go back to the concept of metamaterials, I just want to quickly introduce one other concept, that is of plasmons. What are plasmons? They are collective electronic oscillations. So if you have a metal and you have a dielectric, so these have two different refractive indexes. And if there is any electronic oscillation at this particular interface between the metal and the dielectric, that is a plasmon. And there are basically two types of plasmon: propagating surface plasmons for thin films, which are continuous, and localized surface plasmons if you have nanoparticles. This is majorly the concept of plasmons. And plasmonics is being used nowadays a lot for fast photonic devices because we want much higher speeds of photons to be transmitted from one side to other, and the size of electronics is reducing. So we need much faster photonic devices with lowest losses. So I would request, if you have unmuted yourself, if somebody is unmuted, can you please mute yourself? Or in INYAS office, can you help in muting them? Maybe it is on because of some other reason. So there are many applications of plasmonics as such. So you have a plasmonic cloaking device, that is, you can hide things behind certain kind of metamaterial plasmonic devices. Then you have hotspots. If you want to do sensing, you will create these kind of hotspots between two plasmonic particles, and this particular region will be a hotspot for sensing a particular chemical, a biological moiety, or so on. Nowadays, people are exploring various theranostic applications of plasmonic nanoshells, where they are doing targeted imaging therapy and targeted chemotherapies, which have nanoparticles, which have linkers to it, and they go and attach selectively to a tumor cell. And then by giving an IR radiation to that particular region, these skin cells are not damaged, but the tumor cell eventually has so much heat in it that it finishes. There are applications nowadays where, if you remember from our childhood, we used to see these antennas, Yagi Uda antennas, aluminium के होते थे, and we used to see these. और आजकल उसके बाद डिश आया बहुत बड़े वाला, उसके बाद धीरे धीरे ये डिश मिनिएचराइज हुआ, and now the future is going to be, you'll have just a small chip box which these kind of nano antenna arrays, which are metamaterials, which are working in the electromagnetic regime, where we get the signals from the TV broadcasting services, and they are going to pick it up and supply it to your TV, your mobile phones, or projectors in the future. And they are going to be as small as this. There are next generation photovoltaic cells, because we always need energy harvesting, we need energy generation, and we need miniaturization. And these are the alternate solutions that we are going to get when we use plasmonics and metamaterials. Of course, in biosensors, it's a great use. And of course, nowadays we are talking about not just lasers, which was actually the 1960s. It is the last greatest achievement of humankind, was the invention of lasers. Uske baad koi itni great invention nahi hui hai abhi tak. So surface plasmon lasers or spacers and an alternative for lasers, but it's not a great achievement because lasers have already been invented. So there is nanotechnology everywhere around us. If we just look around us, we can see nanotechnology. Agar aapne arbi ka patta dekha hai ya lotus leaf dekha hai, it never gets dirty and it is never wet. You can see the particles of water on it, but it never gets wet. So seeing these, people took it for scanning electron microscopy, and they saw that they have these kind of nanostructures on it. And seeing this, we had an idea, the scientists had an idea, and it can be used in day-to-day applications like non-wetting or non-dirty getting clothes, textiles, and also textiles that don't need washing. You just dip it in water and they are clean. And this was the idea. And nowadays these are commercially available. Arrow, be it Park Avenue, be it Reebok, everybody has one of these variety of textiles. Also, when we talk about high-rise buildings like Burj Khalifa, who is going to clean the windows? A human is going to hang from the top floor and clean the windows. It's going to be a very difficult task and also risking human life. So seeing this, how the lotus leaf keeps itself clean, how the shark keeps itself clean, the scientists came up with the idea that if we have nanostructures on the window panes, automatically when rains come or water falls, it cleans off the window. And this is the technology of self-cleaning windows. Furthermore, the scientists have seen the feet of the spiders or water striders, that they can walk on water. They can take their own weight and they can walk over water. And when they looked closely into the feet, they saw microhairs, and they saw nano grooves inside these microhairs which trap air And that is why they give them a buoyancy effect. And according to the size of the animal, if the weight is larger like a gecko, or if the weight is lesser like a beetle, the sizes of these microhairs and nano grooves, they have to be reduced so as to take the weight of this particular insect or a reptile. So you can imagine, if we want to lift ourselves as humans, we need much smaller sizes even than a gecko, because then only we'll be able to create that kind of vacuum, that kind of buoyancy effects. Coming back to the metamaterials, when I was talking about the negative refractive index. So let's just revise the parameters of permittivity and permeability, epsilon and mu. So if we talk about dielectrics like water, air, glass, these all are dielectric positive materials. That is, epsilon is positive and mu is also positive. And they always have a forward propagating wave in it. Now, when we talk about mu negative materials, they are usually magnetic materials like iron, cobalt, and they have an evanescent decaying wave. So it decays as it propagates. And similarly, in metals, you have an evanescent decaying wave where epsilon is negative. In metals, please remember that epsilon is negative, whereas mu is positive. All these three kinds of materials are easily found in nature. But when mankind was looking for these kind of materials where epsilon is negative and mu is negative, that is dielectric negative materials, and it will have a backward propagating wave, not a forward propagating wave like the dielectric, but a negative or a backward propagating wave, and these are not found. And how can these be made? It was a lot of debate, a lot of theoretical calculations that went into it. And eventually, theoretically, it was proved that if we can mix certain kind of mu negative materials in certain shapes, and the metals, which are the epsilon negative materials, if we can mix them together in a certain way, that we can keep the mu negative part from the mu negative materials and the epsilon negative part from the metals, and we can combine these two, we can get the DNG materials, that is the dielectric negative. And because it is much easier to fabricate larger sizes and centimeter sizes, because all PCBs these days are being fabricated that way. So these kind of materials were being fabricated and were first fabricated for the radio wave frequencies in the centimeter range. And once they were fabricated for the centimeter range, they could easily be miniaturized, and now they could be written onto a circuit board with split ring. These kind of systems are known as split ring resonators, and these are the metallic rods. And when combining these two, we get a metamaterial. So here we are not talking about the atomic structure. Mind you, I'm just reminding you once again, we're talking about the bulk structuring of the material. So that means the innate properties of the material still remain the same, but the overall properties of the materials, they change just because of the external structure and not because of the composition. So don't think it's the mixture of gold and iron alloy or something like that. It's not an alloy. There is no chemical interaction going on here. It is just the physical placing and the arrangement of these particular structures together. And theoretically, many different structures have been already talked about, discussed a lot, and they are being used very well when it comes to the radio waves, because it's much easier to produce them because centimeter sizes are easier. But when we talk about the visible range, what is the visible range? It is from 400 nanometer to around 750 nanometers. Now, if we want that the light interaction for these metamaterials should take place in the visible range, which is visible to the human eye, then we would like these structures to be in the size of nanometers. So it has to be below 200 nanometers. And fabricating this, that becomes a little bit challenging, and you'll have to go for photolithography, e-beam lithography, where you're writing with electrons or with photons, so as to get this kind of structure sizes. And the metamaterials can be made in any of these whole electromagnetic regime, just the size has to change. So if you are at larger frequencies, larger size like centimeters is fine. If you're going lower sizes, then you have to go to nanometers, like in the visible range. If you want to work with X-ray metamaterials, you'll have to go even beyond maybe atto or picos meters over here. So my question to you, now that you know about plasmonics and you know about metamaterials, is, have you seen Harry Potter? Have you seen the bionic eye of the Terminator? I am looking forward to some answers now from the audience. Have you seen it?
Yes, ma'am.
Okay, great. It was my childhood movies, and that is why I'm showing it here. Right? I'm not sure if you guys have seen it. So in Harry Potter movie, you have a cloak where Harry Potter puts it on his body and he's invisible, right? And the bionic eye of the Terminator can really focus on his target and exactly pinpoint where he's shooting. So do you think this can be reality or it's all fiction? What do you think? What is invisibility?
Doable.
Doable, but it is very tough job for a scientist. Yes. So when we talk about microwave invisibility or negative refractive index materials, it has been done. It's completed because of the structure sizes. And we were able to show that the material beyond this is invisible. And how is it? If you have air here, you have a metamaterial here and an air here, and you have an object here. And if its image is being focused here, then you get a image in near field and no longer in the far field. So it's invisible to that particular person who is beyond it. And when we talk about sub-wavelength imaging, nowadays we have these Google lenses and so on. They are made of these kind of tiny structures and mesh of different pixels that can be connected to your front part of your cornea, and that can focus it onto your retina, and hence leading to this kind of focusing, which is doable. So what different types of metamaterials are available? The best metamaterial available in nature itself is your butterfly, the peacock wing. They have beautiful colors. And if you look closely into this, they have periodic grating structures. And because of this periodic grating structure, different periodicity gives a different color. When you take a CD disc, you can see, if you just take a CD disc, if you just move it a bit, you'll be able to see various colors. And it's because the light is interacting with the grating, which is similar to a prism, and it splits the colors. Red is bent differently and blue is differently bent, and that is why you can see these colors on a CD, which has grooves on it or gratings on it. And similar kind of gratings have been found on butterflies, on peacock wings, and humans have refabricated it. We have tried to make these kind of gratings to get these kind of colors. So optical metamaterials which work with electromagnetic waves are working with plasmonic absorbers, photonic crystals, which give different colors, negative refractive index lenses, and of course, metamaterials. Then there are acoustic metamaterials. I'm sure if you have visited a cinema hall, I'm sure everybody has visited once for sure. Not in the past 3 years, I don't think so, but you might have seen a cinema hall and you could have seen these kind of various structures around the cinema hall, which have huge structures to absorb the extra noise that is going out of the cinema hall. So if you just walk outside the cinema hall, you cannot hear what's going in. Aapko nahi pata chalega andar kaun si wali movie chal rahi hai. But if you get into the cinema hall, it creates a, what is it called? It's a bass sound that it gives in constructive interference for the audience inside, whereas it's destructive when it comes outside. So these are photonic crystals or photonic structures and acoustic lenses structuring that is being used, which creates these kind of properties which are not found in nature. These are not just optical or acoustic, which are waves, but also mechanical in nature. So if you might have read little bit of propagation of waves in metals, you might be knowing the wave propagates very fast in metals. So when I visited one of the cathedrals in Vatican City, there is a cathedral where if you are in the main hall and you speak anything, it can be easily heard when inside a priest's room. It's because they have these metal bars that carry these waves, and it was designed long time ago. And this was already known to them that the speed of sound is much faster in metals than in air. And now we are talking about mechanical metamaterials, where we are talking about a negative Poisson's ratio. That means if you pull in one side, it does not reduce in the other, but it pulls on both sides, it expands, its volume increases. And a very simple calligraphic kind of example is given here. So if I'm pulling this system, its volume is actually increasing. It's staying same, but its delta L by L is increasing. So the Poisson's ratio is increasing, and it has a negative elasticity and bulk modulus. And similarly, if you have certain fluids, which will have these kind of systems, which the fluid flows and the compressibility of the fluids are negative, then it is known as the metafluid. So similar concepts are used in optics, acoustics, or mechanical engineering. And these are the metamaterials which have properties not found in nature. So what is the application of this metamaterial? Invisibility, of course, is one of them. And you can easily paint them on fighter jets, and it will not be visible to your radar system. You can get stealth paints on planes. And how does this stealthing work? Is basically when an incoming radar wavelength is incident on the aeroplane or any air drone or something like that, it reflects it back to the detector. But what we want is it does not reflect back, but it absorbs it. And this type of absorbing metamaterials are being used here. Because normally if radar is sending a signal, it goes into space and there's nothing that is reflecting it back. So it is lost in space, and that is why it says there's nothing in the sky. So these are the applications which are of use when it comes to defense applications. It is of great use when we talk about surgeries done by hand. At times when a surgeon is doing surgery, his hands are actually creating blind spots, and that can be avoided if we have gloves which have metamaterials on it and it is visible to him what he's seeing. Furthermore, many of the accidents occur when we are driving cars due to blind spots, those areas in the corners which have blind spots. And of course, bionic eye, night vision, camera lenses, very high transmission of satellite antennas, information transfer. These are the futuristic applications of metamaterials, and you're going to see them in the coming 20 years. So when we combine the plasmonics and the metamaterials, we will see much smaller devices, much faster devices. We'll see these kind of structuring. These are real metamaterials that you are being shown here. These are the structures of nano-sized metamaterials, which are being integrated by the nanoprocessors and your photonic devices. These are the nano antennas which are being used in the satellites sent to Mars rovers, to Mars missions, to moon missions. They are sending these kind of devices for sensing of the soil, their chemical composition, and so on. Nowadays, in future, you will see your teeth decay will be monitored by these kind of structured devices or metamaterial based devices, which will be connected. These antennas will be connected to your apps in your phone. And if your dentures are lost, supposedly for old people, if your dentures are lost, you can always vibrate it and find your dentures. So this is a little bit of work from our group on metamaterials. I'm not sharing much of it because of the time, and structuring is very important. And that is why you can increase the amount of light that goes into your solar cell. So structuring is not just important for biological or these kind of applications, but also for the existing applications. We are all going through a pandemic currently also, that is SARS-CoV-2. And the diameter of this virus is around 100 nanometers. So it's in the nanometer region. So we are looking always for various kind of detection techniques which are non-invasive. We don't want invasive techniques. And so if people have started already working since the day one of 2020 of the SARS-CoV-2, and they have found of various methods in which they can use nanoparticles, where the detection can be made by naked eye. And nowadays we can easily find these antigen kits, which we can use at home and check whether we are positive or not. And similarly, not just for SARS-CoV, but for influenza, rhinovirus, HPIV, we have Raman spectroscopy that can be used for the enhancement using these different kinds of nanoparticles, these different kind of structures, which will enhance these signals of the Raman sensing. And with this, I would like to thank you for your kind attention, and I hope I am in time. And yes, thank you for your kind attention.
Thank you so much. Thanks a lot, Neha. This was a wonderful talk, very basic, and I thoroughly enjoyed it. If there are any questions from audience, I think we have time, and we can take them up now. You can either type them on chat window or perhaps unmute yourself. So there's a question in chat window, Neha, from Keithana. Shall I read it?
I'll read that. How is it made certain that there will be any negative effects on the body if used in dentures or other body parts? Thank you for your question. Actually, it's just an antenna. So if you have an antenna in your house and you're watching TV or you're using a mobile phone, it's the same negative effect that you will get when you're using dentures, not more than that. And it's much smaller and it's much smaller in size, so you'll not be getting that much of the negative effect. So when we talk about electromagnetic radiation, it's usually we are talking about much larger wavelengths, and that are much longer than even the humans, so it does not affect the humans as such.
Okay, thank you. Any more questions? Meantime, Neha, are you doing all this work experimentally, or there are some kind of theoretical calculations also involved? Like,
see, when we talk about metamaterials, it is directly going to experiments is just
too risky.
अंधेरे में तीर मारना. So we will have to do some theoretical calculations so that we can narrow down the range of our structure sizes, our periodicities, our material. We have various parameters that we have to play with to get an optimum give and take between the for ENG and MNG materials, and then we bring them together.
So first there are preliminary calculations and then you
Yes.
do the experiment. So it's a combination of both.
It has to be done, and it's an iterative process. Sometimes the experiment does not work even though the computational work is fine. And we have to go back with that data and input that.
So there's one more question from Anuj.
How to differentiate metamaterials from nanomaterials? Firstly, why would you want to differentiate a metamaterial and nanomaterial? In any case, they are very different things. So nanomaterial is something whose structure size is small, that is in nano range, right? So that is a nanomaterial. If its nano range is around 10 nanometer to around 200 nanometers, that is the nanomaterial size range. So when we talk about nanomaterials, either its dimension in all 3 dimensions has to be in this range, or in 2 dimensions, or in 1 dimension, it's called a nanomaterial. But with metamaterial, the important point is the structure size can be in any range. It's the important thing is the periodicity. So the periodicity has to be in line with the incoming electromagnetic radiation. So whatever radiation you want to work with, whatever wavelengths you want to work with, that has to be the periodicity relation with your metamaterial. So if something is periodic and it works as a negative refractive index for that particular electromagnetic regime, then it's a metamaterial. So these two things are quite different. Not all nanomaterials are metamaterials, and not all metamaterials are nanomaterials. So both things are very different.
Can you fabricate these nanomaterials in labs, like make your own? Oh, right.
Yes, yes, you can do it using E-beam lithography. You can use electron beam lithography. That is, you etch away the parts in your substrate, using electrons, or you can use photolithography as a templating mechanism to structure your substrate and then fill it with the another material using sputtering or deposition techniques like spin coating. Depends on what is easy for you. If you want in the visible range, in much larger range, a PCB manufacturer को आप structure दे दीजिए, he'll make it for you and give it to you.
That's interesting. Okay. And finally, if there are no questions, then there's one more question. Maybe perhaps you can answer that first.
After BTech in electrical PCE, is there any career option to be placed in nanotechnology to do a job in this field? Well, firstly, EC is a very broad field. So if you want to get into nanotechnology, you can easily get into it because you have a lot of electromagnetic characterizations that we require. We require still innovation that requires quick and faster analysis of nanomaterials if you're interested in that. When we talk about jobs in the field of nanotechnology, currently in India, you will find more on synthesis and production with the job market. So until and unless you have an experience in fabrication, jobs in nanotechnology are a bit difficult for a person who has not done synthesis work. But yes, if you are into devices for nanotechnology, you will be hired immediately. Can data science play a role in developing efficient materials? Yes, very much. Data sciences and materials are very important. So if we look back last 200 to 300 years, any new material development took around 60 to 70 years because it was a hit and trial. They were mixing different things and a new materials were born at times by hit and trial only. But eventually by the development of data sciences, that is, we input the data into the computers using various softwares, integrating with the artificial intelligence, which is also one of the important fields nowadays that I have started working in last 3 years. We input the data of various materials, their parameters, and how we can mix and match all these material properties and find a new materials which is much more efficient, having another new important property like a magnetic property or an optical property or some other mechanical property. And the whole time scale of development of this particular new material has been reduced from the 60 to 70 years to another 5 years. And eventually, if the AI is going to play an important role and we're able to tune the different parameters, the whole new material development and if efficient material development scale is going to even reduce maybe 6 months or 3 days also. It depends on the efficiency of the program. So data science is very important.
Yeah, last question. I think we are running out of time. So maybe this last
is there any sort of immune rejection of metamaterials in case of human body? Are you talking about the very first slide that I showed about imaging and therapeutic targeting? If that is the case, then these are gold nanoparticles, which are non-invasive to the body, and they are in a shell. And they have linkers, which are biolinkers, which go into the body. So your body actually is not interacting directly with this nanoparticle, but the linker, which is biocompatible, is going and targeting the tumor molecule and selectively creating hotspots and heat in that region. And eventually the whole body will reject it through our normal rejecting system. So it usually does not amount to immune rejection because we are working with the whole setup of biocompatible materials here. So another 2 questions, I think, is there any role played by chemistry in this meta and nanomaterials, and can chemistry BSc graduate pursue nanotechnology? Well, chemistry is, I would say, the father of nanotechnology or the mother of nanotechnology. If you have a background in chemistry, or if you have a background in physics, if you have a background in mathematics, if you have a background in engineering, any basic degree, you can go into nanotechnology. So any basic degree, if you're good in your own field, you will be good in nanotechnology, because nanotechnology uses the inputs from all these 4 fields, and then only nanotechnology has been developed. So yes, you have a lot of opportunities to pursue nanotechnology. I think the Zoom
there are
meeting is
no-
going on fine. So
Yeah, that's right.
right. Lucky, we are lucky to have this. And it has not cut in.
That's nice. Students had a lot of questions, and my last question was exactly related to what Vaibhavi asked. Like, what background do we need for students to pursue what you are doing right now? And you perfectly answered that. So, are there any more questions? If yes, you are free to unmute yourself and interact with Neha. I guess not, but your email address I saw is available on the website, IIT website. And
Yes.
participants, students have any other further questions? I hope Neha
Yes.
won't.
Yes, Shri Vashni.
I have a doubt.
Yeah, please.
Thing is that what are the characterizations that one would do for this metamaterials, generally nanomaterials?
See, firstly, what you want to see is whether the structure that I have made is really what I have made. So firstly, seeing it. So you'll have to go for SEM if the structure sizes are in few micron to say 200, 300 nanometers. If it's lower than that, you'll have to go for FESEM. If it's larger than that, then you'll have to go for an optical microscope. First thing that you want to see is what I have made. Is it really the same structure sizes? Once that is confirmed, you need to go ahead and see the materials that I have made during the synthesis process. Have they changed somehow? You might have to go for XRD or UV spectroscopy or FTIR or Raman, depending upon what materials you're using. Usually they are metals, so you cannot use Raman or FTIR. So UV at times is used because you want to see if the transmission through this metamaterial is good or not. If it's in the visible and the UV region, the transmission. But if it is in the higher range, the radio frequencies, then you'll have to go for a vector network analyzer and analyze the transmission and absorption in that particular electromagnetic regime. So for each electromagnetic regime, you have different devices, different characterization techniques to do the same transmission, absorption, and reflectivity measurements. If you are looking forward to the mechanical properties, then you'll have to go for nano indentation. And basically for metamaterials, you have to build your own setups to characterize them. They are not commercially available, but they are quite easily characterized if you have that kind of bent to make your own setups.
Thank you, ma'am.
Any more questions? So if not, thanks Neha, thanks a lot. It was a wonderful talk, and I am so happy to see more females coming and giving talks and motivating. That's really motivating for me at least, and for others as well. So it was a very nice talk, very motivating to see you doing such wonderful work, such a nice profile and such wonderful research background you have. And I also thank INYAS for providing this platform, which is of huge, and this is a good opportunity for all the students who are attending these talks. So thanks so much. And I guess I'll see you next week for another session.
Thank you, Vindhyari. Thank you.
Okay. All right.
Thank you. Bye.
Thank you, professors.